In this video, I'm going to illustrate the central limit theorem, which says that the mean of a large number of measurements randomly sampled from a non-normal population is approximately normally distributed. And at first glance, that theorem might not seem to be a big deal, but in statistics, this theorem is a huge deal, and the results that it gives us enables us to do a great many statistical tests and other techniques, and almost everything that we do in this course you can trace it back to the central limit theorem as kind of the underlying theory that makes the technique work. And so it's a huge deal in statistics. And so I'm going to illustrate that theorem with data on the Spanish flu. And so I'm just going to load the data, and then actually let's take a look at it so we can see what it represents. And so this data is the frequency distribution of age at death in Switzerland in 1918. And what we can see is there's a peak in the distribution right on the left hand side of the age. So this represents infant mortality, this peak on the left. We've got another peak for older people. So again, that's very typical for this kind of distribution. Is we're seeing age at death peak in this case at around age 73, 74, 75, somewhere around there. But what's interesting here is we've got a third peak for people who are dying in their 20s and 30s, which ordinarily you wouldn't see this. And so you might think, well, the First World War is going on at this time. But this is for Switzerland, and Switzerland was not involved in the war. And so this peak in the middle is not young soldiers dying in the war. This is young adults in their 20s and 30s dying from the Spanish flu. And so it's a very interesting population distribution, this. And it's clearly not a normal distribution by any stretch of the imagination. Normal distribution has a bell shape, and this is about as far from a bell shape as you could imagine. So what we're going to do is we are going to think of this as the population. So ordinarily in statistics we don't get to see a population, we only get to see a sample. But for teaching purposes we're going to consider this as our population, and then we're going to sample from it and take a look at those sample results and see if we can see any kinds of patterns in the samples. So let's I'm actually going to start with a sample of size 1, which might seem a little bit odd, but let me just do that, and then we'll be able to see what's going on. So this code here, it's running a loop, and it's taking a sample of size n from this population, and then it's calculating the mean of the age in the sample. Okay, so in this case we've got a sample of size 1, so we're just picking one of these observations at random and recording its age, and then we're doing that 10,000 times. So you might think that's a little bit odd, but bear with me because it's going to illustrate a point. So see if you can guess what the histogram is going to look like for this sample. Okay, just think for a second what we're doing. We're taking one of these observations, recording its age, and then we're repeating that process 10,000 times. And what I'm going to do now is I'm going to create a histogram of those sample ages. What do you think it's going to look like? Okay, well, bonus points if you thought it would look exactly the same as the population one. So that should make sense to you, because all we're doing is sampling directly from the population, and our sample size is 1, so we're just recording the age. So the sample distribution looks exactly the same. Okay, let's mix things up a little bit, and let's try a sample of size 2. Okay, so I'll run that. And let's think about what we're doing here. So now, let's go back to our population. So here's our population. I'm picking 2 observations at random and calculating the mean age and recording that and repeating that process 10,000 times. So I'm going to have 10,000 numbers in my sample, and they're going to represent the mean of 2 observations from here. So for example, at random I might pick age 23 and age 57. Okay, and then I would add 23 and 57 together and get 80, and divide that by 2 and get 40. So I would record 40 as my mean age for my first sample. And then I might pick 2 more, and I might get one of these infant mortalities at 0, and someone at age 50. And so I add 0 and 50, divide by 2 and get 25. So I would have 25 for my next value. Okay, and then now I'm going to create a histogram for that distribution. So again, just take a moment and imagine what the resulting histogram would look like. Okay, so let's take a look, see if you're right. Wow, so looks very different. Okay, it's beginning, even though our sample has only gone to 2, our sample size, it's already beginning to resemble a symmetric bell-shaped curve, kind of starting to look normal. This isn't completely normal looking because it doesn't have that classic bell shape, but it's reasonably symmetric. There's still a bit of a peak on the left with the infants, because those were overrepresented in the population. We had lots of infants dying, and so we can imagine in our samples, a lot of the samples are going to have a 0 in them, and so that's why we're getting this peak on the left. So this peak in particular is representing samples where we happen to get 2 infants in our sample. But otherwise, it's starting to resemble a normal distribution. Okay, let's go up to a sample of size 4, see what happens. Okay, so I'll do my sampling, and so now what I'm doing is from this population I'm picking 4 observations, calculating the mean age for those 4 observations, recording that, and then repeating that process 10,000 times. And my sample means, so I'll give you a moment to think about this as well. What do you think the sample histogram is going to look like? Okay, well, bonus points again if you thought that it's going to really start to resemble a normal distribution now. Okay, and it's very much like the classic bell shape. Let's just let's jump now to a sample size of 64. Okay, this is going to take a little bit longer. Actually, it didn't take very long at all. I've got quite a fast computer. And let's look at the histogram for that. By now, you should anticipate that when I click run here, we're going to see a histogram that's, to all intents and purposes, normal. Okay, so yeah, there it is. Actually, let's change the bin width a little bit in that, so that we get a little more detail. Okay, there we can definitely see the classic normal distribution there. Okay, so the other thing to notice here is that so the central limit theorem is telling us that the mean of measurements randomly sampled from a non-normal population is approximately normal, and we actually know from theory what the mean and the standard deviation of those sampling distributions are. So in particular, if we think about where the mean is here, we can see it's kind of right around here. So what is that, like 40? It's not quite 45. It's maybe not quite 44 either. It's maybe 43 point something. Okay, somewhere around there. Actually, I guess we can calculate it, right? Let me just get the right code here. Yeah, let's take a look. Mean of results. So this is the sample mean. There we go, 42.23. Okay, and what was the mean of the population? So I just want to make sure I get the code right. So the population variable is called flu age. Okay, very close. Okay, and it's because we're taking quite large samples by now, sizes of 64. We're doing that 10,000 times, and so the mean of those sample means is very close to the population mean. Theoretically, it's exactly the same. The mean of the sampling distribution is the same as the mean of the population. Okay, what about the standard deviation? So let's just think about that for a second. So we can get a visual impression of the standard deviation by thinking about, remember, if we have a normal curve, if we went out one standard deviation from the mean on either side and thought about the area under the normal curve between mean minus one standard deviation, mean plus one standard deviation, we'd get about 2/3 of the total area under the curve. Okay, so and another way of thinking about this is if you think of that classic bell shape, you could think about tracing it here, and so the curve is going one way, and then at some point around here the curve starts to go the other way, and then it comes over the top and it's curving this way, and then somewhere around here it starts to curve the other way. Imagine if this was a road and you were driving, you would have to be steering left to go on this part of the curve, and then you would have to be steering right to go on this part of the curve, and then you would steer left again. Okay, the point where you start to steer the other way, that's one standard deviation away from the mean. Okay, so in this case, what is it going to be? So we had the mean at a little bit over 43. The curve is starting to go the other way at, I don't know, 20, not 20, 30, 38 maybe. So maybe 5. Let's check that on the other side. If I went 5 up from the mean, I would be at 48. Okay, I think the standard deviation is going to be a little bit less than 5. I guess we can find out. So let's calculate the standard deviation. Okay, I guess I was a little bit off. 3.29 is the standard deviation. Okay, so if you go 3.29 this way and 3.29 this way from the mean, that's where the curve starts to go the other way, and that's where you would have about 2/3 of the area here. What about the standard deviation for the population data? Is that also going to be 3.29? Well, if you just think about that for a second, let's go back to our population distribution. What do you think the standard deviation is here? Okay, it's a little harder to think about because we don't have that nice interpretation of going one standard deviation away from the mean because we don't have a normal distribution in the population. But do you think the standard deviation here is 3.29? Well, I hope you're saying to yourself, yeah, no way. Okay, standard deviation is way bigger than 3.29. Let's find out what it is. Yeah, 26.34. Okay, so looks like there isn't that direct correspondence between the mean of the sampling distribution and the mean of the population. Looks like the mean of the sampling distribution is a lot smaller than the standard deviation of the sampling distribution is a lot smaller than the standard deviation of the population. Okay, but there is a relationship. Okay, and the relationship is that the standard deviation of the sampling distribution of the sample means is given by the population standard deviation divided by the square root of the sample size. Okay, so that's the result here, and this quantity has a name. It's called the standard error of the mean. Okay, and the formula is given by the standard deviation of the population divided by the square root of the sample size. Okay, let's do that calculation just to see if it's borne up by our experiment here. And so the sample size for this last run that I did was 64. So when I do this, I'm not going to get 3.290786 exactly, because we took a random sample. There's a little bit of random error in here, but it should be close. Okay, and sure enough, it's close. Okay, so that's an illustration of the central limit theorem.